Is 2024 December 6th of December. We will talk about linear algebra. The key things first is when in problem there are conditions such as ax equals to b, which is vector 3 by 1 vector. Has no solution, then we can use no solution information, which will have rank is smaller than 3. This is what we give. Second thing is ax equals to b, which is vector 0, 1, 0 has exactly one solution, which means unique solution always means for no free variable. Free variable didn't make new solution. Free variable can't be new solution. It can be just add dimension on null space, and we can then add all variable pivot variable. It is different with full pivot. Full pivot, which means n by n matrix case. Full pivot means it can be in n by n case. It should be r equals to n, which is number of rows. So in this case, R should be same with n, and we have things that ax equals to b, one vector 1, 1, 1 has no solution. The rank should be smaller than 2. 3, when the rank should be smaller than 3, then n has only 1 or 2. That is option. And second thing is, let's say it again. In this case, what further information can we get? First is ax is linear combination of a and x, and which is also this linear combination of columns. So there will be number of columns here. And with this, we can further search the proposition, which is ax equals to b has solution for each b, which means there will be b, and b should be in column space A. Then we will be not able to represent with this picture because column space A should be super large, and we can let's move to least square problem. Let's say column space A is just its second dimension, and there is B. If theta equals to 0, we can say consistent, but we don't know if it is unique or not because we need pivot columns information. But there is no information of pivot column. This picture gives just B is whether in column space A or whether it is not in column space A. And with this, we can make alpha plus beta x y equals to a plus bx, which is convertible with b equals to ax linear algebra problem. Y equals to a plus bx when theta equals to 90, which means even you orthogonally projection this, you can't explain anything about b hat. In this case, x is independent with y, so beta equals to 0. It will be x, y. The line will be like this. In this case, r squared equals to 0. This will be also one projection. Diagonalization is another key. We should think about it, but I will cancel it right now. Just think about how it is working here. And there is proposition ax equals to b has a unique least square solution for every b. For each b. For each b, in this case, also ax should be super big. So we can use a should be linearly independent, and the matrix A transpose A is invertible. Ax equals to 0, then we can first use Ax equals to 0 if and only if A transpose Ax equals to 0. And we can also use null space A equals to null space A transpose X. Now we'll talk about orthogonal relation, which is row space A is complement of orthogonal complement of null space A, and column space A is orthogonal complement of null space H transpose, which is if we do dot product each other, then they will become 0. But for any vector in column space A are orthogonal to vectors in null space A first, because if we transform this sentence, then this is this equation, and there can be, we can easily find an example. If we make vector matrix which is 1 1 1 0 1 0, then in this case basis of column space will be 1 comma 1, but we can make basis of 1 comma 0 0 comma 1. 1 comma 0, then in this case, 1 comma 0, then we can make counter example with basis null space as 0 comma 1. In this case, 1 comma 1. Where's this? What can be counter example? Oh, 1 comma 1, 0 comma 0, and there will be 1 comma 1. Basis of column will be 1 comma 0. And in this case, we can make null space as 0 comma 1 or 0 comma k, whatever. And basis of null space can be -1, 1. So in this case, column space is 1, 0. Null space is -1, 1. There is counter examples. And for orthogonal set, let you want to use P be an orthogonal basis of subspace W Rn for each y in W, which is in like if it is subspace, then there will be y can be presented as there will be subspace W, and there will be y. It can be represented as each weight, and each weight is determined by this. This is very similar with orthogonal projections. Orthogonal gram sheets. We do x1 equals to v1, then xk equals to x2 equals to v2, v1 equals to x1, v2 equals to x2 minus v1 not v1. x2 v1. It looks very similar. And for last, there's proof problem, which is if A is positive definite, which means positive definite is symmetric matrix and eigenvalue is all positive, then x1, x2, x3, x multiplied by A, matrix A, multiplied by x1, x2, x3 transpose is always positive. This is related with quadratic polynomial formula. Let's make it like this. There will be vector x1, x2, x3. And we can write A as this because it is matrix A is definite matrix, one of the type of definite matrix. So we can orthogonal diagonalize. So there will be unit vector and there will be eigenvalues. Then we can write this portion as y, vector y, which says y1, y2, y3. Then we can write it as y1, y2, y3. Then it will be come out like this. Then this will be all the term is composed of square and eigenvalues, so it will be positive. Thank you very much today.